Bismillahirrahmanirrahim. So today we'll be talking about the another spectroscopic portion, that is the vibrational spectroscopy. Fine. So vibrational spectroscopy, today we'll be dealing with the basics of the vibrational spectroscopy. So it's also called as IR spectroscopy because this spectroscopy you actually observe in the infrared region. So in this spectroscopy, again I will focus that since I'm dealing with the basics, I'm trying to finish the course in terms of, you can as your course is objective type examination pattern, so I'm not going deep into it, but I'll give you the basics of it. So in vibration spectroscopy, what actually we do with the radiation we use is we are using IR radiations, fine, infrared radiations. So that means when we talk about the interaction of electromagnetic radiation, the matter here, which is called as spectroscopy, the radiation used is the IR radiation, number one. Now once we instant this radiation, जब भी हम इस radiation को इस्तेमाल करते हैं और it strikes the matter, it's absorbed, so it results in some change. So that change is that it results in vibration in molecule. What do you mean by that vibration in the molecule? अगर molecule vibrate कर रहा है already, then its vibration will increase. It's to and fro motion, back and forth. ठीक, the vibration that gets increased. और हम ये कहेंगे the molecule goes from one vibration energy level to the next. अब ये vibration, we can say it in the simple terms, it is like stretching and compression. Stretching and compression. इसको हम ऐसे अंडरस्टैंड करेंगे that in terms of classically, अगर हम classically इसको अंडरस्टैंड करने की कोशिश करें, that no, the vibration spectroscopy basics, classical approach. So we assume that when the molecules absorb the infrared radiations in the classical approach, they undergo stretching of the bonds or they undergo compression of the bonds. उसके हम क्या करेंगे? So we'll take example of a diatomic molecule. ये diatomic molecule like HCl or whatever. So that diatomic molecule so now we have, it's like अगर इसको bond के हिसाब से दिखाएं तो HCl bond. तो यहाँ पे in this spectroscopy we assume that it behaves like a spring. So this is your mass M1, that is hydrogen. This is mass M2. So we assume that the bonds, they behave like these springs. Now, if you stretch this spring, for example, you take it from this position to this position. Now this position to this position. Well, now this is your extreme position, fine. So you are stretching on both the sides. Likely release the spring gets compressed. So you may have this type of so the situation, from one situation, the compression and the expansion situation. The expansion situation is like this. This is expansion situation. And when you talk about the compression situation is like so this is your compression situation, fine. So you are basically now this is the normal molecule, this is called as the equilibrium position, ठीक? So if we say this distance, this is the equilibrium distance, this one. The equilibrium position होगी इसकी. अब ये जो इसका position होगा, this is going stretched. This is one type, and this is compression, fine. So this is your compression situation. ठीक है ना? तो this is your compression situation. So this is one type of distance now, new interbond length. This is another R. तो यहाँ पे जो molecule originally था, this is the atoms were at the equilibrium positions. अब हमने इसको stretch किया and then we are releasing that matter and going compression. अब देखिए bond length change हो रही है ना. तो this stretching and compression back and forth, ठीक है ना, This is called as vibration. So it's going from mean position to the extreme position, extreme position, extreme position. So क्लासिकल अप्रोच में हम वाइब्रेशन स्पेक्ट्रोस्कोपी में भी यही कहते हैं कि the molecule the infrared radiation interacts with the matter or your molecule, it absorbs the radiation and undergoes stretching and compression back and forth. This is called a classical approach. तो हम ये कहेंगे the infrared spectroscopy, when the matter absorbs the radiation, it undergoes vibration. So that vibration can be stretching and compression. So याद रहे कि you are dealing with a classical approach. इसका मतलब है we can use the formula called as the Hooke's law. तो हम Hooke's law का यूज कर सकते हैं यहाँ पे Hooke's law. और Hooke's law मतलब force is directly proportional to the displacement. कितना डिस्प्लेस हो जाएगा एक बॉडी फ्रॉम द मिसाल के तौर पर अगर यहाँ से हम देख लें ये वाला ये पोर्शन, दिस इज x1. थोड़ा सा what is the duster? Yeah. यहाँ से हम मान के चले अगर हम this portion check this portion, this one distance, this is x1. इस तरह से यहाँ पे this much has been compressed, this is x2. तो हम कहेंगे ये जो x है it is how much the bodies are getting displaced. So I can say x is equal to x1 plus x2. तो जितना हमने डिस्प्लेस किया, जितना हमने बॉडी को स्ट्रेच किया, accordingly the restoring force gets developed and that restoring force is directly proportional to the displacement, जिसे हम Hooke's law में कहते हैं. तो हम ये कह सकते हैं that the restoring force is equal to kx, or this is the force constant, or it can give us the strength of the bond. So the force constant. The force constant more means the more restoring force will get developed. ठीक है ना? So we can apply the Hooke's law when we consider in the vibration spectroscopy when we are talking about the classical approach. ठीक है ना? F is called kx. This is the force constant. ये force constant बहुत important quantity है. This we'll discuss. मिसाल के तौर पर, if we have two bonds, for example, three bonds. You have C single bond C. We have C double bond C. We have C triple bond C. Again we'll discuss this later, but यहाँ पे just basics. इस case में it's a triple bond, it's a stronger bond. So if we see the force constant is K3. In this case, the force constant will take as K2. In this case, if we say force constant is K1, so since it's a stronger bond, the force constant will be more in this case. So we can say that your K3 is greater than K2 is greater than K1. So the force constant is more in this case. So that means your force constant is more, restoring force will get more developed. और हम ये कहेंगे कि this molecule, इसमें आपको ज़्यादा force चाहिए to stretch. And I can say if it interacts, if this molecule, if this bond interacts with the radiations, its vibration frequency will be more. तो क्योंकि vibration frequency is given by, again we'll go to the vibration frequency which has been derived classically. So this is very important. The frequency with which molecule vibrates. So vibrational frequency. Vibrational frequency. The frequency with which a molecule vibrates. Let us say it's a diatomic molecule, जैसा कि हमने बनाया. The vibration frequency is given by, I will not go deep into it, I will put the vibration in terms of wave number. Wave number हमने पहले ही देखा, it is 1 by wavelength. इसका unit होता है centimeter inverse. So that vibration frequency is equal to 1 by 2 pi c under root of K by unit is centimeter. This is your vibration frequency. Your vibration frequency, which is inverse of wavelength, and unit is centimeter. 1 by 2 by c is the velocity of light. K is the force constant, and nu is the reduced mass. So K is the force constant. जो हमने यहाँ देखा force constant, that's K. So reduced mass में पहले भी देखा, reduced mass is equivalent to so m1 m2 divided by m1 plus m2. तो अगर reduced mass आपका कम है, the vibration frequency will be more. अगर यहाँ important जो मुझे बोलना है, that is your wave number of vibrational frequency that is directly proportional to the under root of force constant. तो अगर force constant ज़्यादा है, the bonds have more vibrational frequency. तो इसके हिसाब से, that's why I was saying, क्योंकि it's a triple bond, its force constant will be more, so its vibrational frequency is more. So you can see the vibrational frequency here 3 is greater than vibrational frequency of 2 and then vibrational frequency of 1. तो ये तो हो गया आपका classical approach कि when the matter interacts in front of radiation, it undergoes vibration, stretching and compression, so it behaves like a spring. For example, this is a diatomic molecule. That means we can apply the Hooke's law. We can calculate the vibrational frequency as per this approach. So the vibration frequency is directly proportional under root of force constant and is inversely proportional to the reduced mass. So it behaves, इसका मतलब ये कि यहाँ पे हम एक molecule behave करता है like a spring, ठीक है ना? अब then what is the energy? तो energy also we know. So we can use the energy of the classical approach of the energy. That is the so the potential energy, you can calculate potential energy. So the potential energy is given by 1 by 2 k x square. ठीक, और x जिसे हमने पहले कहा, x जो है that is, अगर x हम यहाँ वो क्या, that is ये जो extreme position पे गया molecule from this end to this end. So this total distance, this is r minus equilibrium, जितना stretch हो गया distance x, so that is r minus re. So that's your x. So potential energy, कितना potential energy gets इस molecule का है, that depends on कि जितना ये ज़्यादा it will go to the extreme position. So the potential energy will get stored in the molecule when you stretch the molecule. Fine. So the potential energy of this vibrating molecule, which is in this case a diatomic molecule, is given by 1 by 2 kx square. So the potential energy is given by 1 by 2 kx square. अब हम in nutshell, I will just brief this class that in the classical approach, in the classical mechanics, as far as the infrared spectroscopy is concerned, interaction of higher radiation in the matter, it leads to the vibration of the molecule. Or if molecule is having less vibration, it starts vibrating with a greater frequency. Vibrating means the molecule behaves like a spring. ठीक? So it starts the back and forth vibration. It gets increased. So it starts initially the molecule is vibrating like this. Please look at my hand. So when it absorbs the radiation, see the vibration frequency increasing. और हम यही कहेंगे कि the molecule goes from one vibration energy level to the higher vibration energy level. So that portion will come in the quantum approach. Inshallah, that will start tomorrow. ठीक? So at the moment we see that molecule, as per the classical approach, behaves like a simple harmonic oscillator. So as the classical approach is concerned, in the vibrational spectroscopy, molecule behaves as simple harmonic oscillator. So when it behaves as simple harmonic oscillator, so that means the Hooke's law will be obeyed, where the restoring force developed is directly proportional to x. See? And then accordingly we can calculate the frequency. This is the vibration frequency of molecule, so which is directly dependent on the bond strength and depends on the mass, inversely to the mass. So this is all for the day, the basics of vibration spectroscopy. और last point यहाँ पे याद रखिए कि range, कौन से कितना range होता है इसमें absorb करता है, that is usually 4000 to, ये important रहता है exams में, around 667 centimeter inverse. ये आपका vibration spectra जो है, it will be around this. Molecule absorbed from, the molecule will absorb from 4000 to 667 centimeter inverse. तो यहाँ पे today, in today's lecture, so what we are concluding that interaction of higher radiations with the matter leads to the vibrational change the molecule. अब हमने यहाँ पे it is the stretching. अब दूसरा concept ये है कि it can be the bending. अगर molecule bend हो, for example, our molecule हो, it's like a water molecule. So the molecule can also undergo the bending like this. तो हम यहाँ ये कह सकते हैं, we can assume that so you are basically having this kind of concept. So these are the two atoms, two hydrogen atoms. This is the oxygen. So molecule undergo bending also, and the molecule can undergo stretching also. For example, stretching up this and this. Same as they get the stretching up this and this. But overall, it behaves like a spring, a simple harmonic oscillator. So this is all for the day, the basics of vibration spectroscopy as far as the classical approach is concerned.